All right, we're going to keep talking about these limits at infinity. Remember, these are limits when x is approaching infinity or negative infinity. And in our last video, we talked about how these limits are really telling us about end behavior. And so we looked at things like power functions, and I think we looked at some transcendental functions. And we're going to just keep moving along forward and think about a couple more function types. So in this video, we're going to investigate some polynomial functions and rational functions. And again, we're going to be thinking about the end behavior of both of those things. So let's get this started. Here's a reminder of what a polynomial function is. Remember, these c sub k's are all just real number coefficients. And then we multiply those by variable x raised to some exponent. And we call n the degree of our polynomial. All of our exponents are just these nice non-negative integers that we have. Cool, so this is a polynomial function. What we'll notice is that these polynomial functions are really just combinations of power functions that we talked about in our last video added together. So it's a good idea to notice that, but it also is a bit of a bad idea to follow that line of thinking too far. We have originally, with our limit rules, that the limit of a sum is the sum of the limits, meaning if we have all of these things added together, we can break this apart and look at the limit of each term individually. And that might feel like a pretty nice thing to do. But what we'll notice is that this limit is just a constant, but all of these other limits are limits of power functions, and these are all positive or negative infinity, depending on what the coefficients are, what the degree of the term is, whether x is approaching positive infinity or negative infinity. What that means, though, is that we would have a sum of infinities and negative infinities. And that ends up being a really tricky thing for us to deal with. We'll find that later in the semester. We'll have some ways of building up and figuring out what things like infinity minus infinity are. But infinity minus infinity is one of the hard philosophical math problems that we as a humankind have struggled with for a long time. So we're not going to try and recreate all that work. What we're going to do is we're going to notice that this is a sum of power functions, and we're going to do things a little bit differently. So what we're going to do is we're going to find a common factor for this, which sounds wild to think about, because when we're finding common factors, you're probably thinking something like this: 2x cubed plus 4x squared plus, 6x. And we'd say, oh, look, 2x is a common factor, right? All of the coefficients are even, so that means 2 is a common factor. They all have x's in them, and so x is a common factor, and we're left with something like x squared plus 2x plus 3. Did I do my arithmetic right? Cool. That's what we're normally thinking of as a common factor, that if we were to undo this by doing the distributive property, we would just end up with where we're at. Now, it is really hard to find a common factor for this polynomial because we don't know what any of these coefficients are. Some of these coefficients might be 0, which means that there could be a common factor of x in here, maybe not. We're not really sure. Some of these coefficients might have common factors, maybe all of them do, but we don't know that because we don't know what they are. Well, what I'm going to do is just disregard any of that uncertainty, and I'm going to say, let's find a common factor anyways. What we're going to do is factor out x to the n. And we're just going to pretend it's a common factor. What we're really going to do is divide all of our terms by x to the n. So here we go. I've just gone and factored x to the n out. You would notice that if I did the distributive property and multiplied this all back in, all of these denominators would end up getting canceled out, and we'd have an x to the n right here still. So we do end up with the same polynomial. Now, this is a little weird. It seems a little strange to be doing this. What I'm also going to do now is notice that I've got x's in the numerators and denominators of almost all of these terms, right? The only one that I don't is right here. There's no x in the numerator on this. What that means is that I can reduce these fractions by doing some weird subtractions of exponents and stuff like that. So you'll notice that I have one x in the denominator of this, I don't want to say first term, it's really the second one, but the first interesting one. I've got 2 x's in the denominator of the next one, 3, 4, 5, and then all the way till the end, we're going to be dividing by x to the n again. Okay, now what we're going to do is use those limit properties that we had earlier. Instead of at the very beginning breaking this up into a sum, we're going to break this up into a product now. So we're going to look at the limit of x to the n, and we're going to look at the limit of the rest. And then we can break up that into a sum. What we'll notice is that now all of these terms here have x's left in the denominator, right here. And what you might remember is that if these are reciprocal power functions, when x goes to infinity, all of these terms are going to go to 0. So now we don't have things like infinity plus infinity minus infinity, things like that. What we have is this constant, c sub n, whatever it was, plus 0, plus 0, plus 0, plus 0 forever and ever and ever. Well, that's pretty great, because what that means is that we just have these two limits multiplied together. I'm going to pull my limit statement back out front, and we'll notice that we're just left with the limit of the biggest term, the nth degree power function. Okay, so what does this actually mean? This means that for polynomial functions, if you're looking at a limit at infinity, we can really just focus on the largest exponent term. Well, that's a little strange to say, but what we'll notice is that this matches up exactly what we know from end behavior, right? If we were to talk about the end behavior of this polynomial function, what you would do is you'd say, okay, this is a 7th degree polynomial, so I know it's odd degree, so that means my end behavior is going to go in opposite directions. And also, we've got a negative coefficient out front, so it got flipped upside down. So it's probably going to look like this. Oops, I need to get rid of my straight line tool. Something like this. And it'll be like bouncy in between, right? We don't really know exactly what's going on there. To find out more information about that, we'd have to be able to find all the zeros and blah, blah, blah. But for the end behavior, we know that this polynomial function looks like this. That's because the limit as x goes to infinity of f of x is really equal to the limit as x goes to infinity of just negative 4x to the 7. Odd degree, negative coefficient, bang, we're good to go. We could do the same thing as x goes to negative infinity here. So for end behavior, this is an old result that we know, but now we can show is true about polynomials. The limit as x goes to infinity or negative infinity of any polynomial function is really the same thing as just considering the largest degree term. Okay, so if we know how polynomials work, let's think about rational functions. Rational functions are just polynomials divided by polynomials, right? So we'll say p of x and q of x are both polynomials. You'll notice I've got different letters for the degree on each and different letters for the coefficients on each because they might be different, right? And what we're going to do is set up a limit to find the end behavior. Now this is going to go really nicely because we know that the numerator function and the denominator function are both polynomials. So we set up our limit. I'm going to write in my definition of what these polynomials are. And now we're going to do some old limit properties. This is a limit of a quotient. So that means it's going to be the quotient of the limits. So we'll toss the limit on the top and the bottom. But you'll notice, wait a second, these are all polynomials, right? So don't we only have to consider the biggest degree term of each one? Isn't that what we just did? So sure, let's look at just this biggest degree term. And now what we can do is just bring that limit statement back out front. We can say the limit of the quotient is the same thing as the quotient of the limits. We have quotients of limits, so let's write the limit of the quotient. And then if you want, you can try and reduce this fraction, right? So it's really like x to the m minus n, but I think probably this is just an easier form to look at for now. Once we actually have those coefficients and have those exponents on x written in there, then you can reduce things. And you'll notice you're left with a power function. We know how to analyze power functions. So there's our big result that we have. If this function is a rational function, p of x and q of x are polynomials, then the limit at infinity, whether it's positive infinity or negative infinity, is really just the same thing as the ratio of the largest terms here. Here's some examples that we can look at. What we'll notice is that our biggest degree terms are not always the first ones that are written, right? So 4x to the 5 is our largest degree, and negative x cubed is the largest degree on the bottom. So what we can say is that the limit as x approaches infinity, for instance, of f of x is equal to the limit as x approaches infinity of 4x to the 5 over negative x cubed. And now this is what I mean by just reducing things later. It's easy enough to see that this is really the limit as x goes to infinity of, what's this, negative 4x squared. And now we can think of this as like an upside down parabola we're looking as x goes to infinity, so we're looking at the right side end behavior, right? Move this way, looks like it's going down. So this limit is negative infinity. Similarly, if you wanted, we could look at the limit as x approaches negative infinity of g of x. It's the same function, just upside down, right? I looked at the reciprocal instead. So you'll notice this is really the limit as x goes to negative infinity of negative x cubed over 4x to the 5. Well, we can reduce this fraction again. And what you'll notice is that we're left with negative 1/4 x to the negative 2, or the x squared is in the denominator. This is a reciprocal power function. Those go to 0 when x goes to either positive infinity or negative infinity. You might find a case where the degree on top and bottom are the same as each other, in which case maybe after they reduce, we just are left with a constant. Limits of constants are just constants, and so we can get this nice end behavior. Remember, if these limits exist, like this one does, that means there's a horizontal asymptote. So keep an eye out for those. We can discuss the end behavior of these rational functions pretty nicely. Okay, so rational functions that are asymptotically linear. What the heck does this mean? This is something that you may have seen before, but maybe not as formally here. So if you've seen this in an algebra class, just bear with me. We'll at least try and describe what's happening using limits. We're going to consider a rational function where the degree of the numerator is larger than the degree of the denominator by 1. So here I've got a quadratic on top and a linear on the bottom, right? Degree 1 on the bottom, degree 2 on the top. The same thing would work if we had degree 5 on the top, degree 4 on the bottom. And you'll see why in a second. What we're going to do is we're going to, oops, I got ahead of myself. We're going to use some long division here to rewrite this. This is almost like if we had a fraction that was like 7/3. You can rewrite this as 2 1/3. I always like to put the plus sign in here because if it's not, this looks like 2 times 1/3. I think mixed numbers are garbage. That's my hot math take for the day. So this is really 2 1/3. We know that because 7 divided by 3 is 2 with a remainder of 1, right? So what we can do here is the same thing. We can do some polynomial long division. Oh boy, that sounds scary. And if we divide this out, we should be able to get some sort of linear function and a remainder. I'm going to pause the video and see if you guys can remember how to do this long division. If you know how to do synthetic division, you can kind of do some synthetic division in this case, although you got to be careful because there's this coefficient of 2 on the linear piece. Maybe that's ringing some bells for you, maybe not. But take a break, pause this video for a second, see if you can get through this long division and remind yourself on how that goes. All right, hopefully you've gotten through this long division. Whew! Let's talk it out though. Remember with long division, you're really just trying to think of what you need to multiply this denominator by to get the numerator. So we can think of this term by term. We need to multiply 2x by a factor of x to get this 2x squared to match up, right? And then we do all of our distributive property, multiply x by 2x plus 1. Here we go. I'm doing some subtraction. And then we bring this term down for who knows why reason. Long division is really annoying because it disguises what division is. But again, that's a rant for another day. And then we just keep going. Now to match up with 6x, we need to multiply by 3. So we end up with 6x plus 3. Subtract, we get negative 6. That's our remainder. What that means is that we can write this in the same way that we wrote this mixed number. We have x plus 3, the thing that we got when we did the division. And then here we said plus 1/3. That's because we were adding our remainder divided by this denominator. So we'll do the same thing. This is minus 6 over 2x plus 1. Here's what this looks like. This is x plus 3 minus 6 over 2x plus 1. So first off, I want you to notice, you can see that slant asymptote. This is what I mean by saying this function is asymptotically linear, right? And the ends of our function, we have some linearity happening. So if we want to find the formula for that, we can think about limits. As x goes to infinity, what happens to these pieces? Or more specifically, what happens to this piece versus this piece? So this is what I want us to think about. So let's take a look. Oh, here's zoomed out even further. There you can really see the asymptotic linearity here. We also have a vertical asymptote at -half. That's from the denominator, 2x plus 1. But there's this nice slant asymptote. And if we want to find the formula, the equation for that slant asymptote, we can think about the limit as x goes to infinity. So what I want us to do is just to consider these pieces separately. So I'm going to break this up into two limits. This is a limit as x goes to infinity. And actually, if I wanted, I could put a plus or minus infinity in here, right? I'm going to have x plus 3, and then I'll subtract the limit as x goes to plus or minus infinity of 6 over 2x plus 1. And what I want us to notice is that this term goes to 0, right? We have a power function in the denominator here. You can do a bunch more work to show that this goes to 0, but hopefully we recognize that the denominator is getting really huge, the numerator is staying fixed. We're dividing 6 up into an infinite number of pieces. It's going to get really, really small. So what we're saying is that when x goes really far out in the positive direction or in the negative direction, this function really turns into this linear function, essentially plus 0. So that's why we can see our function start following this straight line here. That straight line is x plus 3. That's our asymptote here. So we can find these slant asymptotes really nicely when we have these rational functions where our numerator is bigger by 1. That's all I've got for this video. In our next video, we're going to take a look at some other cases of limits at infinity, including some weird ones, which will be kind of fun to look at. So hang in there. Hopefully you can knock this stuff out. Remember, polynomial functions and rational functions in general are really nice because the end behavior always acts like the very first terms do, the biggest degree terms, those leading terms do. That's really the main takeaway that we should be taking from this. All right, good luck as you move forward.